Welcome to the final week of this NPTEL course on muffler acoustics. So, we are into week 12 of this course. So, just to keep all of you guys updated, what we will be doing in this final week on this course is basically do a couple of things, do a couple of important things. First is analyze your extended inlet and outlet system using an analytical formulation. You know, all this in the last week we just had a glimpse of 3D analysis where we presented your piston driven model for a rectangular and circular chamber mufflers, where we did side inlet and side outlet end inlet and end outlet systems, and talked about end inlet, side outlet, side inlet, side outlet systems, presented some MATLAB simulations. So, well, what we intend to do really in this week is basically talk about the extended inlet and outlet system, which is basically something like this, things like this. So, we will consider only a circular chamber muffler, and what we do, let us consider this region A, B, C, D and E, and we will follow all the conventions that are presented in Salamet's paper, which I am going to present to you shortly along with this derivation. So, this is an extended inlet and outlet system, as we have been reading a lot about this thing since week I guess 4 onwards. So, there is no perforated pipe. So, this kind of a thing is not there. Okay. This kind of a thing is not there, it is just extended inlet and outlet system. So, all this while in the ever since we presented the system in week 4, we have considering only planar wave propagation, and to accommodate for the higher order mode effects, we used to incorporate some end correction things, basically having the notions that the geometric length, let us say the length is L1 here, okay, the physical length, the actual length, and this is your L2, the physical length. Okay. These end plates are rigid. So, this annular plate is rigid. Okay, that is important. So, the point is that we were considering the physical length L1 and L2, and to physical length, these physical length we were adding something called a end correction. So, the actual length or the acoustic length or the effective length, that was slightly larger than the physical or geometric lengths by certain factor L, let us say L1A, that is acoustic length is L1 plus delta, and fortunately the end correction, that is delta, is the same even at the outlet. So, this was again delta. The idea is that this small to account for the higher order modes effect, this delta term is added, which basically increases the length or the increase the length, and hence it is called the acoustic length. And as a result, the peaks that occur in the transmission loss spectrum, they would occur slightly before than just by considering the length, physical length L1. So, in a very clever, in a very subtle manner, we used to consider the higher order mode effect that is generated at the extended inlet and outlet systems. So, all these things are happening. Now, however, if you want to now the question is that how do you determine these deltas at the inlet and outlet. So, one can do a proper finite element full 3-dimensional finite element simulation, something that we have not covered in this course so far, possibly in the next advanced course on muffler acoustics that I might offer. All these topics, numerical treatment of these mufflers might be considered, will be considered along with some experimental techniques. We will talk about that in the very last lecture of this course, lecture 5 of week 12, final lecture. We will talk more about that. But for now, just tell you, this deltas were computed once the expressions presented in the paper by Chaitanya and Munjal appearing in Applied Acoustics, that was done using 3-dimensional finite element analysis. But there are other techniques also, like analytical techniques, or things like mode matching techniques, numerical mode matching techniques, which is also I have kind of reserved that topic exclusively in the next course. But basically your analytical mode matching technique is something that will be used to determine the overall transmission loss spectrum for such a system, and in the process we will find out we can evaluate this deltas in a from the analytical transmission loss spectrum by matching the peaks, and then one can obtain the corrected spectrum. What we will do is that we will keep the scope of the next 2 or 3 lectures of this week very sort of limited to analyze the simple system and not go too much into detail. So, in this particular week in this particular lecture 1 here, what we will do is that we will set up the system of equations required to do the mode matching, and this might spill over this all these things might spill over to the lecture 2 as well. So, let us see how we proceed. So, these regions are symbolically denoted by A, B alphabets, A, B, C, D, E and all that. They are circular in shape, the ports are circular, the chamber is circular, and everything is considered rigid. So, there is no structural compliance as usual. Now, how about we start writing down the equations, the modal summation solution in each of these regions A, B, C, D and E in terms of the unknown modal coefficient. So, let us begin with the port A, let us begin with the port A. So, what we get essentially is as usual we have our Helmholtz equation in cylindrical polar coordinate system. So, P is equal to, we will not employ rigid wall boundary conditions here or here, I mean in the sense that we will express this in terms of forward and backward travelling waves. So, M is basically your 0, 1 to infinity, n is equal to 0, 1 to infinity, and J M alpha M n R naught R into your, then you will have your E. And note another thing that I want to tell you here, which I sort of forgot, sorry for that, is that this for such a configuration only the axisymmetric mode will propagate. So, what it means that only M is equal to 0 mode, that is Bessel functions, or for in this annular region Neumann functions. So, only with such a thing will propagate. Okay. So, n can be 0, in which case it is a plane wave, 2, 3, 4, 5 and so on. Okay. So, basically cos m theta, sin m theta, azimuthal mode or circumferential modes will not be there because such modes are not sort of excited. Okay. So, we will get this sort of a thing. Okay. And now what we can do is that write down the solution. So, let me just write down the modal solution for region A, which is your P A, I would say P A as R and Z. There is no theta dependence, again I am telling you, and E j omega t is already implied. So, this already means E j omega t. So, I am not sort of writing it explicitly, it is understood by now, that is E j omega t. So, this will become n is equal to 0 to infinity and A n plus. So, A n plus means the wave that goes in the along the positive propagates along the positive direction, and A minus you will see will be the wave that propagates in the negative z direction, and we will follow that convention for all the regions. So, K n, I will tell you what K n is, and A n again this is the negative propagating wave coefficient, and this is your xi n r. Okay. So, as usual j is root over minus 1, so keep that aside, and A n and A minus n r the modal amplitudes. Okay. And for the region A, xi n is just the Bessel function. So, let us write it down. Let me just make some small correction here. Let me call this xi n A, n is the nth modal this thing, and xi A means for the ath region A here, the port A here, and this is equal to j naught, m is 0 here. Now, alpha m 0. So, I will just drop m. So, initially it was m n. So, m n by, let us say the radius of this thing is let us have equal radiuses, let us say A, and A of these ducts, as is usually the case, and the diameter or the radius of this is the radius of this can be, you can think of this as r naught, and actually this can be thought of as small r naught, okay, a small change. Now the thing is this is r naught and now the thing is that we will put directly m is equal to 0 and n. So, we will just drop m, we will just call it alpha m n with the understanding that alpha m n for alpha 0 is this thing is 0 n. So, n can be 1, we can have 0 1, actually 0 0, that is a planar wave which is 0, alpha 0 1, 0 2, 0 3. So, based on the monograph that I have shown, let me just show to you my the Springer monograph, the table. So, in this thing, as we see from this particular, the highlighted, I am not able to highlight, but basically where I am pointing my mouse at, the values shown in red, these are all axisymmetric modes. Other one, these are all the ones shown here, these are the resonance frequency of the circumferential mode, and from here onwards all these modes, for m not equal to 0, m is equal to 1 onwards and n is equal to 1 onwards, you have your cross modes. For m is equal to 1, 2, 3, 4 and n being 0, these are circumferential modes, but we will be considering only m is equal to 0, n is equal to 0, that is a planar wave mode, for which j 0 of 0, that is the argument, in the argument of the Bessel function of order 0 is 0, then you just have unity. So, basically this is a plane wave mode and it comes out nicely mathematically. This is the first radial mode, second radial mode, third radial mode and so on. So, these are the radial modes and that is what we will be dealing with. So, I will straight away write this as alpha n. So, instead of all these we will just replace this by alpha n, n ranges from 1 to 0, 1, 2, 3, 4 and so on, 0, 1, 2, 3 and till infinity. We will consider only the first few modes. So, alpha n by r naught into r, this is your modal summation. Okay. So, this is what we get. Now, j naught alpha n r naught into r. Okay. And now, what we need to do is that we have figured out or expanded the solution for this region, and k n is something that we need to worry about. So, k n, there is no mean flow of course is absent here, I just forgot to mention here, mean flow is absent, or you can just ignore stationary medium is considered. Stationary medium, and now you have your k n. So, what is k n? K n is nothing but k naught square minus your alpha n by r naught square. Okay. So, clearly when, now this is something important, when k, under what conditions do higher order modes propagate? Now, when n is equal to 0, like I was mentioning, alpha 0 is 0. So, k n always propagates, and this is the argument is 1 here. So, xi 0 a is j 0 0, which is 1. So, it is a planar wave mode and k n is equal to k naught. It is very simple to see because alpha 0 is 0, that we have seen from the monograph. Now, when when n is not 0, n is 1, 2, 3, whatever it is, then the real business starts and we are into your proper 3-dimensional considerations. At least the first few modes should be considered, because it is not possible to consider infinite set of the such modes. We will consider only the finite set of modes, say 5 modes in the inlet pipe and maybe 10 modes in the chamber and so on, or in the annular cavity. Let us have some representation n here, and when alpha, when k naught is greater than alpha n by r, that is the excitation frequency is greater than this, or k naught r, once you know f naught, we can know k naught. So, if the excitation non-dimensional excitation frequency is greater than the non-dimensional resonance frequency of that particular mode, say the first radial mode, then the first radial mode will propagate. If not, then the if you have such a thing, then the mode will not propagate. If it is less than n, then it is evanescent. If it is greater than or equal to this thing, then these modes will propagate, it is just about to propagate when this is the equality occurs. So, basically what happens is that if you have greater than k naught is greater than this thing, then there is no problem, it is a complex exponential. What we have is a real number, okay, there is no problem in that. But now when k naught is such that this is less than alpha n, then the trick happens that root over k naught r square, this becomes a purely imaginary number. So, kn in that case we can write down this as root over minus 1 times alpha by r naught square minus k naught square. So, this is this is greater, okay. So, here you will have j times the entire argument, which is of some positive number. So, why am I telling you this? Because j times, so here you will have your purely real part of your purely real part, which is actually exponentially decaying or exponentially growing. So, depending upon the convention that we follow, if we consider this as root over minus 1 as this is j, if we consider this as j square root, we can also consider minus j depending upon what we want. So, however, if we consider this as j, then j times j. So, so basically a n coefficient associated with a n will become minus j times j root over alpha n by r naught square minus k naught square. So, this guy will become a n j square is minus plus. So, something positive, so this is something positive, and this of course is multiplied by z, right. So, this will grow this will grow in over space, and hence this can cause numerical problems. On the other hand, if you have things like this is plus, this is minus, as I was mentioning, if you have things like well, j into j times root over this entire thing into z, that is what it was, then it is j minus something into z. So, this is decaying exponentially. All right, a n minus this thing. So, there is no problem, there should not be any numerical problems with this term, there would be a problem. So, a clever trick which is not quite given in books, but I am trying to present that in a very simple manner, is that let us have a change of variable. When we set up the equations, we will have that. So, such a thing, wherever such a thing would occur, we will not at the inlet pipe, when you have z is equal to L, at z is equal to L the other section, because you see we are fixing the coordinate system z is equal to 0 here for this C part, and z is equal to let me call this z is equal to L3. Now, L1 physical length L1 plus L2 plus L3 is equal to overall length L. This thing will not change even when you put this. So, the effective length will become L minus L2 minus 2 delta, the clear length, or the length between from tip to tip. So, the effective length of clear length will be slightly different, but that is a later part of the story. Main thing is that we are fixing z is equal to 0 for the region here and z is equal to L3 for this region, and then other things will follow. But what I am saying is that at some stage we will have to make a change of variable. When z is equal to 0, then there is of course no problem, this is unity and things will be relatively simple, but for the chamber C we might have to do something different. So, we will come to it. So, this was the story for the duct A, okay. And for duct and annular region, now similar thing would be there for duct E. The solution for the port E, let me deal with that thing in a, since I am dealing with the inlet and outlet ports, how about I just write down the solution for that as well. So, this is R Z and this is equal to n is equal to 0 to infinity E plus E minus xi. So, xi n and xi n E and xi n A are pretty much the same. So, here you have your k n z and KN Z here. So, we get this sort of a thing, and we have this guy. Okay. Now, the same things would apply. Xi n e is nothing but alpha n by r naught into r, and actually I guess I made a small mistake here. This is r naught here, I am sorry, and yeah, everything else seems to be all right, and this is r naught. We get this sort of a thing, and Kn is the same, k naught square minus alpha n by r naught square. We get the same thing. Now, we have this. Now, how about the chamber region? Let's worry about the chamber region now, that is basically C region. Here also, like I was mentioning in the last lecture of week 11, that annular region is included for A, E as well as C. So, the Neumann function will not be there, there will only be Bessel functions. So, under such a situation, the analytical solution for the chamber region, that is C, is given by R Z equal to, this is also the same, except that n is equal to 0 to infinity 1 2 C1 plus, and what was it? Yes, this was n here, n minus j k n, this is the chamber thing, into z you can consider, and c n minus j k n c z, and here you will have your psi n c r. Now, psi n c r is this thing, and k c n is nothing but root over k naught square minus alpha n r naught whole square. Okay. So, well, instead notice the difference here, actually this you can think of this as k n e and k n a. K n e and k n a are pretty much the same. They are the same because the radius of the inlet and outlet pipe are same, but in this thing this is r naught. So, r naught is different. Okay. That typically we consider for automotive muffler expansion chambers of expansion, this ratio can be something like, or the radius ratio, expansion ratio can be really varies from 3 to something like 6 typically, and so the area ratio can be something like 9 to 36 or something like that. But the main trick now is, what do you do for this thing? Now, there is one thing that I want to make it very clear, that this analytical business of analytically finding or analyzing these things will work only for such a configuration when you have a concentric pipe. You have a concentric pipe. So, because it is very simple to apply this boundary condition at r is equal to, for the annular region B, at r is equal to r naught, we are assuming, mind you, the thickness of the wall is 0, that is an infinitesimal wall, there is no wall thickness for this one. Okay. But in actuality, in actual application, you will have certain thickness. So, those effects can be considered sort of in advanced courses, or as more advanced topics. For right now, just for mathematical simplicity, we are ignoring TW, although some authors like Chaitanya and Munjal, they have employed finite element formulation, taking into account the finite thickness of the wall to get the end correction. Okay. So, that they have done. So, what we will do is that we will have to worry about the analytical solution for the region B and D annular cavities. They will be the same, the modal summation at least, based on the length L1, L2, the net pressure field will be different. But again, like I said, this analytical thing is only available, only sort of suitable or amenable to analytical solution if the ports are concentric, because at r is equal to r naught, you have the condition del r of p is 0, and this is also true for r is equal to capital R naught, and the radial velocity is also 0. So, the idea is that we can find out a set of orthogonal function for such a thing. This will so this particular form will remain same. So, for region B and D, for region say B, we have P R Z so this will be the same. Where K P N, so this is this thing where beta n, again beta we have only axisymmetric mode in the annular cavity as well, and your xi n b function, let me write down this guy first. So, this is nothing but your Bessel function, this thing where this is beta n by r by r naught, okay, and here you will have your J1. Now, these are all obtained by some identities for Bessel function, and here you will have the Neumann function for the first time, because you have the origin is not sort of included here. So, this is this, and Neumann function beta n by r naught, okay. We will get this sort of a thing. And what about the other things? You have this. So, beta is obtained by solving this set of equation, and in my previous papers I have listed down for typical values. This is beta n r naught, and this is r naught here, and here we have J1 beta n by n1 and beta n into n1 . So, this equation has to be solved numerically only, okay, for a circular cylindrical chamber with a rigid concentric pass tube. So, this was this was how the Green's function looked like, but we are not really considering the Green's function. The form is the same, J n m is again here I am calling it for m, even for non-zero non-zero values m, that is 1 2 3 4, but for the concentric extended inlet and outlet, m is only 0, and gamma 1 is basically this thing. These are obtained, these values, these beta values are obtained from solving the eigen equation, or the equation subject to rigid wall condition, and for different values of beta I have sort of tabulated some of the higher order modes. So, let me just go quickly to the table and show these things to you. So, well, non-dimensional cut-on frequencies for a circular chamber without a pass tube and that with a pass tube. So, this is essentially you can, instead of a pass tube, it is a basically concentric annular region, and beta is equal to 0.2. Plane wave mode always exists, but let us focus only on the column here. These things are not quite relevant right now. What it means basically is that for the higher order modes, the first radial mode for a beta is equal to 0.2, 0.5, they get cut on at a much higher frequency compared to the circular cylindrical chamber. I mean, for 0.2 is this a small difference, but as we keep increasing beta, the ratio of the inner, that is basically r naught to small r naught to capital R naught value, if this ratio keeps increasing, then we have in the radial modes the excitation frequency keeps getting shifted in the higher frequency range, as it is seen by these values. Okay. So, such values have been prepared also for me, and what we will do is that right now we will just consider this guy, and we will use that, and the modal solution for the region region D will also look exactly like region B. So, instead of B's you will have your D's, D n and E j k d and z and d n minus something something and xi dr. This will remain the same, and you can consider finite set of modes. So, once we got the modal solution, what to do now? How do we proceed ahead? Okay. So, for proceeding ahead we need to have the matching condition. So, right now for the first time after all this background I am presenting to you some matching condition. So, let me draw this guy again. Let us focus only on the extended inlet. This is region A, B and C. So, at z is equal to 0, what we will have is that P A at z is equal to 0 is equal to P C and 0, and because the field continuity must always be satisfied. Over this region here the pressure is the same, and for this one at each and every point the pressure in the annular port just at z is equal to 0 is the same as z is equal to C. Okay. So, we get that. And what about the velocity condition? Velocity is u a u tilde a is equal to, at z is equal to 0 is u c at z is equal to 0. At z is equal to 0. So, we basically get this sort of a thing. So, annular velocity here is the same as the one in the chamber, and in the annular cavity that is also the same. Now, basically what the paper that I am following is the one by Salamet and his co-worker, long time back, published about almost 20 years back or so. I guess it was published, I will show you the paper later, in 1999. So, more than 20 years. But Abom and others, what they have done is that they have used separate equations, Salamet and his co-worker, Salamet in G. They have basically combined these two equations in a certain manner, which we will soon see. So, what we need to do is that just using the modal summation solution that we have derived or explained so far, we will multiply, we will basically do some sort of a mode matching, basically use again exploit again and again 3-dimensional analytical things, or wherever you have a mode matching thing or a piston driven model or a Green's function model, wherever basically one has to incorporate the 3-dimensional effects in such a thing without resorting to a full 3D analysis, without completely discretizing the 3D continua into finite elements, rather just discretize the work on the 2-dimensional problems. We all repeatedly have to make use of orthogonality principle, basically rely on modal summation, multiply both sides by appropriate modal functions, integrate over a certain domain, and if they are orthogonal it is fine, if they are not orthogonal we still have to deal with them. And then what we can do is that once we have this system, now let us go to the solution here. So, what we do, we need to set up the system of equations. Okay. So, this is the paper that I was talking about, acoustic attenuation performance of circular chamber mufflers with extended inlet and outlet by Salamet and G, quite widely cited paper published in JSV, Journal of Sound and Vibration, more than 20 years back. So, there is a formulation that I have sort of presented so far is basically following the work by Salamet only. So, these are the functions that we just saw just now. Now, other thing that is very important of course is the velocity condition. If you go back to the presentation to this thing, you will see that the matching condition really means, where is the matching condition? Yeah. So, we have velocity also that is to be matched, velocity fields have to be continuous, the pressure field also has to be continuous. So, but so far in the modal solution we have derived only the pressure modal summation expansion of the pressure field, but we need to do we need to get that thing for the modal summation for the acoustic particle velocity as well. So, what do? We use the Euler equation, j omega, del t of dou t of u, where u is the velocity along the z direction, is equal to minus dou z of p. Now, once you substitute in this time harmonicity, you get j omega and u is just u, I mean you just solve for the spatial field, j omega or j rho omega minus dou z of p. So, once you know p, because the modal summation solution you already know. The trick here is that you need to be careful with the signs. So, moment you do that, j omega, j rho omega can come down now, and j, once you take minus j k, the modal summation you have your minus j k n z. So, minus j k n you can take common, and here that is why you will get a minus sign, and minus minus will cancel here, and j will also be cancelling. So, you will get 1 by rho omega and k n. So, k n, if it was just a plane wave mode, it would have been very simple, nice clean analytical solution. K was omega by c or c naught. So, omega would have cancelled, and you would just get 1 by rho naught c naught, that is your characteristic impedance. By now, these things should be something like a bread and butter for you. So, but however, in a higher order modes you have u something like this. So, k n is not, obviously it is not k n is not k naught in the general case, it is root over k naught square minus your alpha n by r square root over the entire thing. So, k n, so basically k n you cannot take out of the summation sign, it must remain like this. So, basically let me just zoom this thing for you so that you guys can have a look at it a bit more clearly. So, this is what it is, so this is the one that I am talking about. Okay. So, these this will be valid for any region, only psi function will change, and a n plus and a n minus, that will also change, and the rigid wall boundary condition, obviously this is one thing that I sort of forgot to mention, apologies for that. So, basically if you go to your region, the muffler region at z, if you fix the coordinate system here at z is equal to at this end plate. So, at z is equal to minus L1, velocity ub is 0, because the rigid plates, because the end plates are considered to be rigid, they are not yielding or they basically they do not deform. So, rigid wall conditions will be applied, and there will be, so we have a standing wave pattern set here, and similarly at u d is 0, at z is equal to L2. So, let us get back to our paper and see what these guys have done. Z is equal to minus L1, we have this. So, when you do that, what we do, essentially we have to look, sorry for going back and forth in this thing, but that is the nature of the things. So, we are expressing Bn plus in terms of Bn minus. So, Bn minus is the wave that goes in the negative z direction. So, and similarly Dn plus, so what about the other one, Dn minus, the wave that goes in this direction, is propagated, is written in terms of Dn plus. So, these are some of the clever tricks that you need to do. Now, basically let us get back to our matching conditions. This is obviously another this is one boundary condition, at the other end we just talked about in the annular cavity, that is at z is equal to L2. Here this plate is also rigid, so we get this condition. Now comes the matching condition, which I have just written down in the presentation. So, for we put the modal summation expansion for Pa and Pc, and so how do we go about it? What do you do further to process the equations? Well, we expand Pa and Pc in the modal summation solutions that we have just got, and multiply, as Salamet and Lee mentioned, for the pressure continuity condition, multiply both the sides of the equation 9, that is equation 9 is basically nothing but the first one, and equation 10 is this 11, 12. So, equation 9 is multiplied by the modal function psi as that is for the duct, and this is multiplied, again mode orthogonality will apply. So, you multiply this by a generic function. If this is n, well, if this is let me just get to this one. If this is n, you multiply this by n, here you multiply by n1, you multiply this by n1, and then you integrate it. So, only that mode will survive when n is equal to n1. Okay. So, that is why you are just writing this as only one term as plus and as minus, this for a generic term, generic mode S. Okay. So, or n is equal to n1. So, you can call that S. So, that S mode will survive, and this so and so for multiplying over that, so this we need to integrate over the port area, that is this thing. So, you multiply with r. So, ds is nothing but r dr d theta, and this is a psi function, and using mode orthogonality only this function will survive, and you have only this term, and then the mode function psi a s, and this is integrated, this one with the mode function in this one, that is a Bessel function with a in the larger radius in the numerator, I am sorry, in the denominator, that is basically your this guy r naught. So, psi is this thing. So, essentially what it does is basically you when you talk about this psi thing, what we do is basically integrate, say well, let us say this is alpha n r naught and s, I am sorry, this is 0, alpha s r naught r dr d theta. Okay. Basically, we multiply this by this thing, and so well and then basically only this mode will survive here when like I was mentioning, and here we have summation over entire thing. Similarly, when you multiply with the other pressure continuity equality condition with the function psi b s, so again here you have your only one modal coefficient, as we have explained just a while back, and only that particular mode will survive in the annular region, this one, because of orthogonality, because we are basically considering orthogonality of such function over the domain of the port or the annular cavity. When you multiply, when you integrate, when you multiply with the corresponding function. What I mean is that psi a, when you multiply by psi a and integrate over the port area, so here things will be all right. Here you will have lot of non-zero modes also, that is why you have the summation thing. And similarly, here this is orthogonal over the annular region. So, you have your psi b s, this kind of thing, and again you have a summation. So, there is no problem here, I believe, until this part, because again KBS, this can be again like I said, this can be written as j times root over whatever we are getting, j times whatever we are getting, and with the convention that is followed. What is the convention? So, j is your they have followed the convention that j is root over minus 1 imaginary unit. So, when j square is minus 1 is plus. So, they probably would have done something to suppress the numerical instability. So, we will work with our own codes here. So, this is what they are getting, and these things will be there. Now, and the other condition is the velocity condition, other set of conditions. So, this one and this one. So, what now here the other trick is to multiply let us say this equation with the modal function for the chamber C and integrate it over the port area. Similarly, multiply the other velocity condition, that is this condition, with the modal summation solution modal function for this one, and integrate over the annular area, and then add them. Now, only when you add them, only this particular term survives, and in all the other things, the other set of equations, other terms will be there. Okay. So, this this will be there. Now, integrals designated by this thing are referred to the appendix of this paper. Similar conditions will apply, will be set for the outlet, that is, where is the outlet? Outlet is this part, So, pressure here in the chamber is equal to the pressure here, and pressure here is equal to the pressure right in the chamber D. So, that is how they set P c at Z1 is equal to L c is equal to P e at Z2 is equal to 0. So, they have translated the coordinate system. So, for the port, this port, the coordinate system here is defined in the new coordinate system, Z2 is equal to 0, and Z2 is equal to 0 here for the annular cavity as well, okay, and Z2 is equal to L2 at the outlet port. Now, once we have this sort of a thing, we do the same business for the pressure condition, multiply this with the modal summation for the PE port or PD port, and then integrate it. Only this term, only a certain term will survive in the port and the annular cavity, and velocity you multiply by psi Cs, and then go about adding these things, and only particular mode will survive in the chamber. Now, there is one thing. Now, basically what is happening here is that we want to evaluate the impedance, the transmission loss, this thing. So, transmission loss performance. So, E plus is a wave that propagates in this direction, and E minus is a wave that propagates here in the negative direction where I am trying to point. Okay. So, E minus has to be set to 0. All the modal coefficients E and minus, they have to be set to 0. That is what an anechoic termination is exposed at the imposed at the exit of the chamber by setting the reflected wave coefficients E n to 0. So, this like this the number of unknowns reduces. So, this guy is set directly to 0, this guy is directly set to 0, and once you do that, and you get all these things, and D plus is there. Now, what about you might have some trouble as I was mentioning earlier regarding E j minus this thing or E j this thing. So, what happens is that minus j into j you will get if K c is this thing negative, K c is imaginary, root over K naught square minus alpha n by r whole square. So, you take minus common, minus root over minus 1 is j. So, j is minus 1, minus is plus. So, this is a growing term. So, what we same logic applies here. So, what the clever trick then is that you set Cn let me go to the presentation. So, the trick is that let us set e to the power you have this even in this term, and even in the velocity term you set this guy minus j k c n L3, like I was mentioning. This is LC they have written, I am calling it L3 I am calling. Okay, this entire thing, this Kc is such that it is root over alpha n by r naught square minus r naught, minus k naught, and j. So, j square minus is plus. So, we will call this entire thing as C tilde n plus. We will solve for this guy rather than this thing, because this might lead to numerical issues. Most likely it will. So, C n plus this will, we are setting this here, coming back here. So, well we have resolved this problem, but then other thing has to be done. Now, let us check if we have plus j sign. So, j square is minus in case if K c is imaginary. So, this will be exponentially dying term, it should not create a problem. So, so basically C minus n something, this will be left as it is, but then we have to be careful with the other set of equations. What do we do? Now, at the other boundary conditions, there is something that I want you to understand properly. So, here also we have these 3 equations. So, if we are setting this guy as like this, we cannot increase our number of coefficients. You see how many set of coefficients we have? We have AS minus reflected waves in the inlet pipe, travelling wave, forward travelling wave, negative travelling wave in the chamber, and B minus. So, 4 sets of coefficient, 1, 2, 3, 4, and similarly we have this is set to 0, 5 here and 6, and these two are known. Now, moment we set Cn plus e to the power minus j k c n L3 to other coefficient, 6 will be another coefficient, but then we are increasing unknown variable to 7. Now, we will have only 6 conditions, 3 here and 3 above, 3 sets of equations. So, to resolve this issue, we have to be careful with the other variable. Let us worry about what we are going to do with the other thing. So, Cn plus is something that we have done. So, we need to do something with this variable. What we did now was that we just set this guy C n e to the power minus j k n C L 3 is equal to C n in the conditions at the outlet. Now, but when we should not be increasing a number of unknown variables, because we have only 6 set of equations. Okay. So, what we do is that we do a clever trick. This is the trick 1 that we did at the outlet. At the trick 2 at the inlet is that just multiply this analytically with E j k n C L 3. So, this will be C n plus is equal to C n tilde plus is equal to this thing. So, there will not be any numerical problems, because when this is j, so j into j square is minus and minus k C n L 3. So, this will become exponentially decaying term. So, C n plus is an exponentially decaying thing, and so basically what we need to do really is that in here write in this term C n plus, we will substitute this with C n tilde plus into e to the power j k n L C 3. This we will do for the pressure equation here, this condition here, as well as the velocity condition in this equation here. So, with this we are good to go. We can have different number of constants, we can have different number of constants in the chamber, in the port, and different number of modal summation value n in the modal in the inlet port, as well as in the cavity here or in the chamber. So, basically let us consider, what I mean is that if you go to the presentation, in this thing we can consider, say, first 5 modes here, 10 modes here, 20 modes here, or actually 10 modes here, same, this would not be too different, but or you can have 10 modes here, 10, 10, 10, basically n1 modes here, n2 modes here, n3 here. Generally we consider n2 as equal to n3, that is the number of first few modes in the cavity, annular cavity, and the expansion chamber are considered the same. Inlet pipe, because those pipe diameters are typically quite small compared to the chamber, it's about 40-50 mm for automotive mufflers. So, we consider limited number of modes given the operating frequency and so on. So, basically with this what we will do is that we have set up the system of equations, and they eventually what other thing that I sort of must point out here is that once these things are set up, we have set up the system to determine the transmission loss. Then what we need to do is that the dimensions of the inlet duct are assumed such that the incoming wave A plus is planar and its magnitude is chosen to be unity, and anechoic termination is imposed like I was mentioning. So, we have theoretically infinite set of equations, because n is going to infinity, but we have to truncate it to the first q mode. So, we have typically 6 q plus 1 number of equations, q being the first q mode, first the one means the planar wave mode, and then on the top of that whatever number of modes you want to consider. So, 6q or 6q plus 1, whatever you want to say. So, that many set of equations and that many set of unknown coefficients we have. So, all the things we are solving in terms of A plus, we are basically, one thing that I must kind of clarify here, that is very important, that we are considering the excitation by only the planar wave. Okay. So, A s plus is there, or I would say if you go on the top, A n plus. So, n is equal to 0 will give you the planar wave mode, and there will be no, in the excitation part in the inlet port here, in the excitation domain here, I mean in this chamber for the A region, there will be no what we are doing actually is that we are considering, let me mention this point a bit more clearly. So, A 0 plus is assumed to be unity, A 1 plus is 0, A 2 plus is 0, and so on, and A n plus is 0, but at the same time A minus 1 we do not know, this cannot be 0. Similarly, A 2, these are reflected wave coefficients, this we need to solve. So, all the variables, what are those variables? A, and also of course minus, this cannot be 0. So, A n minus n ranges from 0 to say n 1, B, well, n minus n is equal to 0 to n 2, C C tilde plus, where n ranges from 0 to n 3, C minus n is equal to 0 to n 3, d n plus, where n ranges from 0 to n 2, and your E plus n, where n ranges from 0 to n 1, and E n is 0, of course, like I was mentioning. E minus n is 0, anechoic condition. Okay. So we have that many variables, or we assume all the variables, all the number. If we assume n 1 is equal to n 2 is equal to n 3, then we have is equal to q. So q unknowns, q unknowns, q unknowns, q q q. So 6 q, but if you consider plane wave separately, you can consider q 6 q plus 1, like that. But all these will be expressed eventually as a big matrix, where you have this block of equations, unknown coefficients, b n c tilde plus c minus d n and E n is equal to some coefficients into A, and then we need to invert that matrix and express all these variables in terms of A0, and find out the transmission loss as as given by this expression, including the high order mode. But usually high order modes will not survive in the outlet pipe, they are a small diameter. So this will reduce to the expression given in expression that we have discussed so far. For planar wave, this will reduce to this form. So in the next class, we will do the numerical analysis of such things. Till that time, I'll hang up, I'll just stop here, and I'll see you in the next class, where we'll do some numerical simulations in MATLAB. Thanks.